This is a problem from the chapter work power energy. Let's read through the problem once. Small object is sliding on a smooth horizontal floor. Actually, this diagram is the top view. So object is sliding on a smooth horizontal floor along a vertical wall, and the wall makes a smooth turn by an angle theta naught. Coefficient of friction between the wall and the block is mu. The speed of the object before the turn is u at the starting. Find its speed b just after completing the turn. Does the answer depend on the shape of the curve? The turn is smooth and there are no sharp corners. So let us say at some instant when the block reaches this position, its center of curvature is somewhere here, and this is the radius of curvature. And at this instant, let us assume that the velocity is v and it has made a turn by an angle theta. And the forces appearing here will be the normal reaction by the wall, which will in this case be equal to the centripetal force mv square by r, and there will be a force of friction like this, and the force of friction in this case will be mu n, which will be mu into mv square by r. Now the work done by friction will be negative, and this will be the retarding reason behind the block slowing down. And so the small work done by friction will be minus of f, and in a small displacement d theta, let us say it goes on to travel another angular displacement d theta, then this distance traveled will be r d theta. So minus f into r d theta, which on simplification gives us minus mu m v square into d theta. Now from work energy theorem we know that the small work done or will be changed in small kinetic energy. Okay, so the kinetic energy is half mv square, and so the small change in kinetic energy dk will be given by mv into dv. So change in kinetic energy mv dv will be equal to the work done, and the total work done here is only the work done by the friction. So minus mu m into v square into d theta, and then if we simplify it, m gets cancelled, one v will get cancelled. So on variable se variable we get dv upon v equal to minus mu d theta, and then we put the integration with proper limits. Initial velocity is u, final let us assume it is v, 0 to theta naught is the final angular displacement. On solving it, we get log of v minus log of u. This is equal to minus mu into theta naught minus 0. So log of v upon u becomes minus mu into theta naught, or v becomes u into e to the power minus mu theta naught. So definitely it only depends on the angular displacement theta naught, and it does not depend on the path followed by the particle. So that is the answer to this problem. Hope you get it. Thank you very much.